In this work, we propose reconstructing groups of people with hypergraph relational reasoning, which exploits human collectiveness and correlation to improve human mesh recovery in large-scale crowded scenes. Our goal is to regress absolute human meshes with reasonable spatial distribution from a monocular crowd image. Although immense progress has been made in monocular multiperson human mesh recovery in recent years, the existing methods still cannot accurately reconstruct groups of people from large-scale, crowded scenes due to the mutual occlusion, severe scale variation, and complex spatial distribution. Historically, multiperson mesh recovery methods always focused on estimating a few people in small scenes. The top-down formulation iteratively predicts each person from tightly cropped image patches, which discards the interaction relationships and location information in the original camera coordinates. Alternatively, the bottom-up formulation parses interperson interactions with global pixel-level cues and enables its impressive performance on occluded cases. However, bottom-up methods always fail in large-scale scenes since they require downsampling images to low resolution to satisfy computational constraints. Different from a few people or single-person cases, it is common that the crowd in large-scale scenes shows significant interactive and collective motions. The individuals in the same group even have similar poses. Based on this observation, our key idea is to fully exploit the collectiveness and social interaction in crowds, and promote human mesh recovery in large-scale scenes with a hypergraph relational reasoning. However, the idea faces two technical obstacles. First, without a compact representation, the limited hardware memory cannot afford the relational reasoning for a large number of people. Second, the existing networks can hardly formulate the complex and high-order correlation among different individuals and groups in the crowd. To address the obstacles, we propose a multiscale hypergraph to represent the individuals and groups in different scales, and discard the redundant image features in the relational reasoning. Specifically, given a crowd image in a large-scale scene, we first detect human bounding boxes with an off-the-shelf detector. A backbone network is then used to extract valid high-resolution human features from the original image. With the extracted human features, we infer the graph topology according to crowd collectiveness, and then represent the individuals and groups in the crowd with nodes and hyperedges of multiscale hypergraphs. Subsequently, we initialize the nodes with individual human features, and the message for different individuals and groups can pass through the hypergraph via node-to-hyperedge and hyperedge-to-node phases. After the relational reasoning, the updated individual features with group information in the nodes can be utilized to regress the groups of people with absolute positions. Although the network can produce accurate body poses, the absolute positions may be totally unreasonable due to the depth-shape coupling. For example, a short person close to the camera can get a similar reprojection error as a tall person in the distance. Previous works rely on a known ground plane to decouple the ambiguities. However, the ground plane is not always available in a single in-the-wild crowd image. Thus, we further exploit the crowd cues and propose a crowd constraint to promote more accurate absolute position prediction. With an implicit plane from the estimated crowd geometry, the constraint penalizes unreasonable absolute positions and enforces more accurate body shapes. The experimental results show that our method can reconstruct crowds from gigapixel-level images with accurate body poses and reasonable ordinal relationships. In addition, with the relational reasoning, it is also robust to scale variations and occlusions. The comparisons with the latest works show our method can produce more accurate body meshes and absolute spatial positions. Thanks for watching.